In this video, we're going to talk about chapter 10.1, conics and calculus. This is going to be a review from pre-calculus about various types of conic sections. So our goals are going to be to understand the definition of conic sections and analyze and write equations of parabolas, ellipses, and hyperbolas using their properties. I might also just briefly mention circles when we get to ellipses, since they're related topics and we might have to deal with circles. I have done a whole lot of this in a preparing for calculus series where I used the Apex pre-calculus book. I've also gone over a lot of this in the actual pre-calculus videos that I've made for they would be in the Math 162 or Math 167 playlist. So if you want to see lots more examples of these types of problems, instead of just going over the definitions and things here, but you want to see more practice, go ahead and look at those playlists, as this is a really important topic here before we get into the rest of the topics in chapter 10. So we need to go back and look at how we define these things rectangularly before we can go and try and define them parametrically or with polar equations, as that's going to be one of our goals in this chapter. So what are conic sections and why are they called conic sections? Conic section can be described as the intersection of a plane and a double napped cone. So see the images here below. You're going to see that I took a lot of screenshots here, a lot of images from the textbook, just so I didn't have to draw all these things by hand. Otherwise, you might be wondering what I was drawing. It's a lot better to look at these computer renderings right here. So these main conic sections are the ones here that we're going to be talking about. There are these depressed conics over here, but we're not going to be talking about them because we talked about them way earlier in math. We've already talked in geometry and algebra about points and lines and intersecting lines, and those are depressed conics. But we're going to be talking about these conic sections here, a circle where the plane intersects the cone in such a way where the outline here that's traced is a circle. If I tilt that that plane at an angle so that it comes through one side of the cone but doesn't cross through the other side of the cone, it's going to trace out a parabola here. And this extends infinitely like this. If I tilt the plane so that it goes through both sides of the cone here, just one either top or bottom, but it goes all the way through the cone, then it's going to make an ellipse, which is very related to the circle here. This has something called eccentricity. There's going to be an eccentricity of 0 for the circle because it's not stretched out at all like that. And then the last type of conic section that we'll talk about is the hyperbola, and you see that the plane cuts through both the top and bottom sections of the cone. And this is going to be a type of conic section where we actually have two pieces that mirror each other, because we have a piece from the top cone and a piece from the bottom cone, or top half of the cone and bottom half of the cone. The cone is both pieces. So, all right, let's go ahead and start looking at parabolas. Parabolas are things that we've talked about quite a bit since Algebra 2. We started to talk about parabolas as one of the first non-linear equations we talked about. And we usually talked about those parabolas in the form of y equals ax squared plus b x plus c, and we said that if a was greater than 0, it opens up. If a is less than 0, it opens down. And in Algebra 2, we were mostly interested in the x-intercepts of that parabola, if any of them existed, and we learned the quadratic formula for that. Then we became interested in the vertex of the parabola, and we learned a new form of the parabola with completing the square that looked like this. And our standard form, that we're going to use is going to be based off of this right here. So it's going to look a little different than that, but very close to this. You're going to notice some similarities. So where we had the vertex form here, and the vertex we knew was at h, k. We're going to use that same h and k. We're going to use the same x and y, but we're not going to use the letter a. We're going to use something different here. So a parabola is the set, formerly called a locus of all points that are equidistant from a fixed line called the directrix here in this picture, and a fixed point called the focus right here on the picture that is not on the directrix. The midpoint between the focus and directrix is called the vertex right here of the parabola. It's going to be a minimum point for the function if it opens up. It's going to be a maximum point for the function if it opens down, but we're also going to be able to define these parabolas now that open left and right, which we couldn't do before because y was not a function of x in that case, but we're going to get to define those parabolas anyways. There's a line passing through the focus and the vertex here called the axis of symmetry. And you see that in this picture here, the right-hand side is a mirror image of what's on the left-hand side, and vice versa. There's symmetry about this line. That line is not necessarily the y-axis. It can be, but it can be this line. It will always be this line that passes through the focus and the vertex. I want to tell you about one other definition that's not explicitly defined in your book, and I'm going to draw it here. You're kind of going to see it already, but there's this other line parallel to the directrix and passing through the focus called the latus rectum. And it is this line that I'm going to draw, sketch in blue right here. It's right there. And it's going to touch at two important points there. We talked about this in our pre-calculus videos, why this is important, because this distance here, P, is going to be the same as that distance there. And so anyways, that's we'll go ahead and not make a big deal out of that, but this line is very special because of how it relates to this distance P right here. And it gives us two special points that we can solve for that really help us draw our picture with the parabola. All right, let's go ahead and look at the standard equation of a parabola. I already kind of introduced this, the standard form of the equation of a parabola with vertex HK and a vertical axis of symmetry and a directrix in the form of y equals k minus p, where p is that distance between the focus and the vertex, is given as x minus h squared is equal to 4p times the quantity y minus k. So again, it looks very similar to if I rearranged this and brought the k over. In fact, it is. If I brought the k over, you would see that a right here is the same thing as this 4p. We're going to get that, well, it's like this. Y minus k equals a times x minus h squared. And I want to get the x minus h squared part all by itself over here. It's not a, that's 4p. I have 1 over a. Y minus k is x minus h squared. So 1 over a is 4p. A is 1 over 4p. So, and that's the relationship between those two forms, just so that you understand what's going on there. All right. It also could open horizontally, have a horizontal axis of symmetry, and in that case, x and y switch places, and k stays with y, and h stays with x. So the part that you want to pay attention to here is with a parabola, one of the variables is squared, and the other variable is not squared. And all the other forms that we're going to be talking about, both x and y are squared. This is the only form that has one of the variables squared and the other one is not squared. So get the variables that are squared on one side and complete the square, and then get the things that are not squared along with the constants on the other side and make it fit this form with a coefficient of 1 in front of that non-squared variable. Whatever is this coefficient on the outside is going to be 4 times something. Figure out what that is, and that something that you multiply by 4 to get that coefficient that's on the outside is going to be your value of p. We'll do an example right down here, and I'll show you how that works. And this is an example straight out of the textbook as well. I believe all of these examples are straight out of the textbook. So that should help you be able to go back in the textbook and follow along and look at some of the visualizations, and they have some things available to you in your online version of the textbook where you can see these things working, some animations and visualizations and things like that. So don't always use things straight out of the textbook, but this time I did, so that you can get the extra tools to look in the textbook and see what's going on there. All right. The focus lies on the axis of symmetry, p units, where p is a directed distance. We'll call that a vector later, so that if p is positive and you are in a vertical axis of symmetry situation, it's going to be up away from the vertex in the positive y direction. If it's negative, you're going to move down negative y direction. If you have a horizontal axis of symmetry and p is positive, you're going to move to the right to get to the focus. And if you have a horizontal axis of symmetry and p is negative, you're going to move to the left to get to your focus. The focus is going to be an important point for us in physics, just with applications here. I'm going to try and draw a picture here just to show you why we care so much about parabolas. We use them for mirrors. We use them for microphones, for different kinds of dishes that we want to collect information and things like that, because every single line, every single, let's say this is light, and light is coming in through here, and I want to focus that light. Like with a headlight, I want the light to go straight out, right? So there's this light source that I want to make it so that all the light that comes from this light source that comes out in all different directions. If I do this right, it's all going to come out this way. And every single light beam, no matter which way it goes, it's all going to get focused back this way through through the focus along, not necessarily along that line, but usually along that line. So we do this with more like if you want to put a microphone here to catch sounds that are far away or quiet, hard to hear, something like that. You'll see people on sidelines with parabolic microphones at sporting events and especially American football games, and it almost like you can hear and what's being said in the huddle, and you can hear the hits like they're right there, right next to you, and stuff like that. That's because of these parabolic microphones that they're pointing towards the sound and what's going on in the game. Spies have used them for years to actually pick up on quiet conversations. We'll talk about some other interesting applications of some of these other shapes later, but focusing energy to a single point here is the main purpose of a parabolic shape like that. All right, let's go ahead and look here and identify the x variable as the one that's squared. And I want that to be over here on this side of the equation. And I want the other part to be on the other side. So I'm going to move things around here. 1/2 x squared plus x is going to be equal to, and then this is going to be a negative y plus 1/2. And I just move things around. I left that constant on that side, move these two x values over, move the y over there. I don't want this 1/2. I want to get rid of it so that there's a coefficient of 1 there. So I'm going to multiply everything through here by 2. X squared plus 2x equals a negative 2y plus 1. And then I want to complete the square on the left-hand side. So 1/2 of 2 is 1. 1 squared is 1, and I'm going to add 1 to both sides of the equation. That leaves me with x plus 1 squared on the left. And on the right, I have a negative 2y plus 2. I'm going to factor out that negative 2 so that the y has a coefficient of 1. Like so. And I've just identified that my vertex HK is going to be equal to a negative 1 is what makes that factor 0, and a positive 1 is what makes that 0 there. So then I'm going to have to figure out that 4p is equal to a negative 2. So p is equal to a negative 1/2. So that tells me that I have a vertex here at negative 1, 1. I have a parabola that opens vertically. This opens up or down, and it opens down. Since p is negative. And so my focus is at, leave the x value alone, and 1 plus p gets me to my focus. It's going to be negative 1 and then 1/2. Let's see how I did here. And there it is. So the vertex is at negative 1, 1, and the focus is at negative 1, 1/2, and our p-value was a negative 1/2. So there's the picture, the drawing from the textbook, just so you don't have to look at my bad drawing of that. I will do a drawing at the end so you can see what I'm talking about. I did sketch one of these things towards the end. So now let's move on to the next thing with ellipses. Before we move on to ellipses though, let's just briefly recall circles in the form of x minus h squared plus y minus k squared is equal to r squared, and you had a center at h, k, and you had a radius of r, and I'm just going to tell you that you have an eccentricity, that's a fancy looking E, of 0 for a circle, and your eccentricity here for an ellipse is between 0 and 1. Not included. If I have a line, the eccentricity of a line is exactly 1. So this is a circle. On that side, that's a line. On that side, if I stretched this circle all the way out, then this part would get kind of come and have a limit that would come down and be almost linear. And this piece, as I'm stretching it out, if it's like a stretching it out like taffy kind of, I could stretch it out to infinity. But this piece is going to stretch out to get to, you know, this line. It gets real stringy like that. Like if you stretch taffy out, that's the idea here. Well, if I take the circle and I kind of stretch it out a little bit, either in the horizontal direction or the vertical direction, so that it's elongated in one direction here. That's one way to imagine an ellipse, though there's another like really precise way to actually make an ellipse, and I'll talk about that with this picture in a second. But an ellipse is the set or locus of all points x, y, whose distance is from two distinct points called the foci is constant. Foci is the plural of focus. That's why you'll see focus singular here and focus singular here, but together they're called the foci of the ellipse because foci is plural, focus is singular. It says it's from Latin. Things that end in us, like syllabus, in Latin are singular, and the plural of them would end in I, like syllabi is the plural of syllabus, and alumnus, alumni, so on and so forth like that. All right, so the line through the two foci intersects the ellipse at 2 points called the vertices. So I tried to draw that here, but the vertices are actually going to be on the trace of the ellipse there. They're not going to be on the inside, they're external there. And so this is they're on the boundary. There's a vertex and there's another vertex over here, but they're on this line that goes through the foci. The chord that goes from the center to the edge there is what a chord is. Actually, it's just this piece right here that goes from side to side. This chord right here that I basically just drew to make the vertices. That chord is called the major axis. I have a picture of this down here. I should actually just go to the other picture. And the chord that goes the other way that's perpendicular to that is called the minor axis. So there are the foci. The vertices are on the boundary on that line that goes through the center and the foci. And then they're all on the same chord right here. Vertices, foci, and center all lie on that chord called the major axis. And then there's one perpendicular to that that goes through the center called the minor axis. And I'm interested in this distance here I'm going to call A, and that distance there I'm going to call B, so that the entire major axis is going to have a length of 2A, and the entire minor axis here is going to have a length of 2B. Let's come back for just a second and talk about the rest of this picture up here, and show you that, tell you why ellipses are important. So one of the main reasons ellipses are important is because of orbits of planetary stellar objects. I'll just say stellar objects. And when you have two gravitational forces that are pulling on something like the sun and the center of the universe, that you have, we've talked about center of mass, and we could imagine all of the mass of the universe at a point, and it's pulling on these objects that are not the center of the universe, but the center of the galaxy, let's say, and it's pulling on the objects that are in that galaxy. But then you have the sun is very massive and affects the gravitational pull of everything that is within its orbit, within the solar system. So we're going to have these two foci, these two objects with heavy gravitational attraction, that something is going to be orbiting around these two points. So the best way to actually draw these, and Kepler's law, I think I spelled his name right. There's a lot of stuff about Kepler's laws in the textbook. We're not going to get to that today. We might get to some Kepler's law applications in future videos, and we'll come back to ellipses when we talk about that. But if I were actually to want to draw this very carefully, I'd have cardboard and I'd put push pins on my paper where I want the foci to be, and then I'd have a string that was long enough to go from this focus all the way to this edge there, and then looped around here, and then as it was looped around these push pins, but it was long enough to pull here, I keep my pencil tight as I would keep my string tight with my pencil, and I'd pull, and as this side was getting shorter here, this side would be getting longer, so that these distances would add together and stay constant. This distance plus this distance here to that point would always stay a constant, and we could figure out with some trigonometry and some other things from pre-calculus that this is going to be related to the equation that we're going to give down here, that c squared plus b squared is equal to a squared, or a squared minus b squared is equal to c squared, however you want to write that. So the standard equation of an ellipse, it looks very much like the equation of a circle. I've just divided through by this quote r squared, but r squared is not the same for both of them because there was a constant that was different that was out in front of this part that was x minus h squared, and a different constant that was out in front of this y minus k squared. So when I divide through by what I thought was r squared before, that was constant for everything, since these had ones with a circle, then I'm going to get different denominators here. One of them will be bigger than the other one, and the bigger one, the bigger denominator, I'm going to call a squared, and the smaller denominator I'm going to call b squared. And wherever the bigger denominator is going to tell me the direction of the major axis. So This is a horizontal major axis. It's parallel to the x-axis here, and the minor axis here is parallel to the y-axis. Here, the major axis is parallel to the y-axis, so it's vertical, and the minor axis is parallel to the x-axis, so it's horizontal. We already talked about the lengths of 2A and 2B for the major axis and the minor axis, and that we decide A and B based off of which one is bigger. For an ellipse, that A needs to be bigger than B. So I've already worked this example out, and the prompt here said, find the center, vertices, and foci of the ellipse, and we were given 4x squared plus y squared minus 8x plus 4y minus 8 equals 0. And this is just a real good example of a general form of a generic conic section that looks like ax squared plus bx plus cy squared plus dy plus e equals 0, something like that. That's just a generic form of a conic section. And as we rearrange the terms and we figure out which things are going to be positive and negative, some of these things can be 0, like in a parabola. Either the A or the C is going to be 0, but not both. In a line, you're going to get A and C will be 0, and it'll be a linear equation. If you get a point, then it's going to have x and y, and x squared and y squared will all be 0. It'll just be 0 dimensional. So that's why it's depressed like that, is a lot of those terms go to 0 in those equations. So I'm going to separate my x pieces here, 4x squared minus 8x. I'm going to get them together, y squared plus 4y over here, and I'm going to get my constant over to the other side of the equation. And I'm almost ready to complete the square, but I need to pull out this factor of 4 that I see. That's my coefficient on my x squared term. I need to pull it out from the x squared and the x term and put it out front here. 4 times the quantity x squared minus 2x. Close those parentheses. Open some parentheses over here for my y part, y squared plus 4y. Leave that equal to 8. The things that are in red here are from me completing the square. So when I have a -2, half of it is a -1, and a -1 squared is a +1. So what did I just add to the equation? Because of the distributive property, I added 4 times 1. So I need to add 4 times 1 to the right-hand side. Over here, I added half of the middle number is 2. 2 squared is 4. So I'm going to add 4 to the right-hand side again to balance out this 4. So I have an 8 plus 4 plus another 4. 12 plus 4 is 16. If you remember from my general form here, I need x minus h squared over a squared plus y minus k squared over b squared is equal to 1, or I need x minus h squared over b squared plus y minus k squared over a squared is equal to 1. One of those forms that will show up, but I need to have a 1 on the right-hand side for an ellipse. When I see x squared and y squared together, any of those situations, I need to have a 1 on the right-hand side. So I'm going to divide everything through by this 16 here. 4 goes into 16 4 times. Just leave this denominator of 16. There was nothing to cancel with it there, and that equals 1. Then I have to recognize that these numbers need to be perfect squares of something. So 2 squared is 4. 4 squared is 16. If these had been numbers that weren't perfect squares, like 5, I'd need to write the square root of 5 squared down there. So the center, I'm going to read that straight from what makes this factor 0 and that factor 0. That'll be 1 and -2. I know that I have a vertical major axis here since my a squared was beneath my y part. So my vertices are going to be the y coordinate that I'm going to add and subtract a from. My a was 4, so I've got to leave my x coordinate alone, and I take my -2 minus 4 to give me a -6, my -2 plus 4 to give me a 2, and there are my vertices that are going to lie on my major axis. To figure out where my foci are, I'm going to need to figure out c and use the equation c squared equals a squared minus b squared. Take 16 minus 4 is 12, and the square root of 12 is the square root of 4 times the square root of 3 is 2 square roots of 3, exactly. So that's where I got c was 2 square roots of 3, and I'm going to add and subtract that from the y. Remember that our foci lie on our major axis, so we're going to be moving in the direction of the major axis here with our foci, leave the other coordinate alone. So it's going to be on 1, and then -2 minus 2 root 3, 1, -2 plus 2 root 3. No application problems right now because we did all those in pre-calculus. So this is just reminding you what the properties and the formulas are so we can transform those into some different looking but not different things in a little bit that'll be less rectangular, more based off of trigonometry. All right, so hyperbolas are the next and final type of conic section that we're going to talk about, and this is the one that has the two pieces. As we were saying, it's also going to be the only one that's going to have a minus sign in the formula. Everything else so far has been like circles or something squared plus something squared equals r squared, and ellipses where something squared plus something squared equals 1. Hyperbolas are going to look very much like the formula for an ellipse, only they're going to have a minus sign instead of a plus sign. So I'll show you those formulas in a second, but a hyperbola is the set or locus of all points x, y for which the absolute value of the difference between the distances from the fixed points called the foci is constant. So what does all that mean? That means basically that it follows the idea of the Pythagorean theorem here, and we'll see that in just a second. But what that's telling you is a squared plus b squared equals c squared. That's what that means. So that's a real difficult way to say something real simple that you could say, oh, it follows the Pythagorean theorem because we're going to get right triangles. The line through the two foci intersects a hyperbola at 2 points called the vertices, again, related to the exact same idea as the vertices of the ellipse. And I'll show you why in just a second. Now, we're not going to talk about the major and the minor axis anymore. What was called the major axis, well, what we're going to have is we're going to have an axis where the center and the vertices and the foci are on that axis, and that used to be called the major axis. Now we're going to call it the transverse axis. So it's the axis that we're going to kind of travel along. As we make this shape, we're traveling in that direction, left to right here. So that's a transverse axis there. We're transversing that axis to sketch our two pieces of our hyperbola here. If we had a vertical transverse axis, then our pieces would be opening up and down. These axes have really nothing to do with which is bigger or smaller. It has to do with which piece is positive and which piece is negative, because the negative is going to make a reflection and tell us which way we're going to have our pieces open, whether they're going to open left, right, or up, down. So one distinguishing feature of a hyperbola is that the graph has two separate branches. They actually trace together at the same time. It's very strange to get things in Kepler's law that follow this hyperbolic path, but it does happen. All of these types of conics that we've talked about so far can be types of orbits of stellar objects, of comets and asteroids and things like that. So if you had something that was a parabolic path, it would, pass through the solar system and pass out, never to come back again. But if it was elliptical or circular, it would keep coming back in a periodic uh, uh, pattern, like Halley's Comet or something like that, that had this every so many years, it comes back and we can watch for it, right? And if we had this hyperbolic pathway, kind of the same thing, it almost looks like it's two parabolas. They're really not parabolic, but they kind of look like that. And so if I was tracing along one of these, then I would come in and pass out, never to come back again. All right. Standard equations of the hyperbola. The standard form of the equation of hyperbola with center hk is given as either x minus h squared over a squared minus y minus k squared over b squared, or and that's if the transverse axis is horizontal. Then we'll have that, and it could be x minus h squared over b squared minus y minus k squared over a squared. I think I wrote these so that both times the y part was negative, and that's not right. So the idea here is that this can be y minus k, and this can be x minus h here. And the a part is going to stay with a, and the b part is going to stay with y. But this one is that the x part is positive and the y part is negative, and this is the y part is positive and the x part is negative. Sorry that I was trying to edit stuff that I had written before and didn't edit it all the way right. So that's what you want, is that you want this to say x minus h squared over a squared minus y minus k squared over b squared equals 1, and you want this one to say y minus k squared over b squared minus x minus h squared over a squared is equal to 1. Keep the a part with the x and keep the b part with the y for the hyperbola, and don't get it mixed up with ellipses where a has to be bigger than b. It doesn't. Just a is the part that goes with x, b is the part that goes with y here. And so if I have, let me see if I can draw this picture here. If I have a transverse axis that's horizontal, the way that I imagine this is that my mirror here is along the line y equals k, because that's the part that's negative. And real bad drawing here, but I imagined if this was a plus sign, it kind of was an ellipse that opened, and it would matter which one was bigger or smaller. So don't worry about that. I'm just going to draw an ellipse here. I'm going to choose that it's stretched out horizontally, and I'm going to draw the line through its center that's vertical, and imagine that to be my mirror. So there's going to actually be lines here that I'm interested in that box in this ellipse. My asymptotes will go corner to corner there. And I'm going to stay between my asymptotes, but it's almost like I took this piece and reflected it out from this line here, but keep it between the asymptotes. And then keep this vertex here, open this out, but keep it between these asymptotes. It's the best way that I can tell you that to graph, but you've got all this junk that wasn't really part of your graph that you're going to have to erase to get rid of and just see your hyperbola when you're done. So make all those marks that you need to get your asymptotes, and you might want to leave your asymptotes as part of your boundaries for your hyperbola. Just and we'll see a sketch that I made later where this one would open the other way, and I'd have maybe even the same asymptotes here, but instead it would have opened this way and this way. All right. Speaking of asymptotes, I already told you about a squared plus b squared equals c squared is how you can find the distance c, which is how far the foci are away from the center. So they're actually going to be, you have in an ellipse, you had center, foci, vertex. In a hyperbola, you have center, that's not part of your graph, vertex, and then you have foci. Like that. And that's why it's opening towards the focus that's on the outside there. Did not mention this before, but we'll mention it now. I talked about eccentricity of everything else, and the eccentricity of a hyperbola here is going to be greater than 1. So check that in the book. I'm pretty sure that that's correct. So if you have a formula to find the eccentricity using the general form of the conic, and you can plug some numbers in and you can find the eccentricity and tell what the conic is without doing anything else other than finding the eccentricity. So, all right. Each hyperbola has 2 asymptotes that intersect at the center of the hyperbola, and the asymptotes pass through the vertices of the rectangle of dimensions 2a and 2b with its center at hk. There's a real good picture. I drew a rough sketch just a second ago. There's my box that I was drawing to kind of say that you can imagine that there's this ellipse that was in here that this box is defined by, and that I'm taking, drawing corner to corner here to get my asymptotes, and then keeping those vertices of that ellipse there, but turning the pieces out away from the center because the foci are on the outside now and they stay between the asymptotes. All right. If you want the equations of those asymptotes, they're going to come in the form of y equals k plus b over a times x minus h, and y equals k minus b over a times x minus h, so plus or minus b over a here if the transverse axis is horizontal, and y equals k plus, and then these switch places, a over b, x minus h, and y equals k minus a over b, x minus h. The transverse axis is vertical. So now let's sketch the graph of this hyperbola. 4x squared minus y squared equals 16. Again, you're going to want to get this to be equal to 1 to fit the form. So divide everything by 16, and we get
1 over 4, and we get 1 over 16. We don't have an h and k to c because they're 0. So my a is 2 and my b is 4. And c squared is going to be a squared plus b squared. So c squared is going to be 20, making c equal to 2 root 5. My asymptotes are going to be y equals, and because this one is going to have a transverse axis that is horizontal here, since that's the positive part, then my asymptotes are going to be y equals plus or minus b over a, and b was 4 and a is 2. 4 over 2 is 2, so I get y equals plus or minus 2x. I've sketched a graph here where each tick mark has a value of 2, and I kind of drew this box here. Draw it there for you, where that I have the vertices that I know are going to be at 2 and -2. If I start at my center of 0, 0, and I go up to right 1, down to left 1, that's a slope of 2 just because these are the same scale. Up to left 1, down to right 1, and I get these diagonal lines that I can draw here for my asymptotes. I'm going to keep my hyperbola pieces between these asymptotes of y equals -2x and y equals 2x. Each piece is opening towards one of the foci here, and this focus is at -2 root 5, 0, and this focus is at 2 root 5, 0. Root 5 is a little bit bigger than 2, so I estimated it as there's 4 and a little bit more, and there's, -4 and a little bit more, and there's 4 and a little bit more. And that's just where I eyeballed those foci to be. So there's my rough sketch that I told you that I was going to make, just so you could get to see how to draw something by hand. Your calculator is not going to be able to draw these things in rectangular mode because they contain y squared things lots of times, and it can't graph those. The only one that it's going to be able to graph is a parabola that opens up or down, but you're going to have to use your other form that you had before was ax squared plus bx plus c equals 0, and then it can graph it. And it's really not to your advantage to switch back and forth between those two modes just for graphing on your calculator. Use a graphing utility like Desmos. GeoGebra probably can handle it. Something like that that's going to be able to take the equations in the form that we learned them here, and be able to graph them for you. Also, any higher level graphing utility like Mathematica or Maple, anything that uses those mathematical engines behind it, is going to be able to graph these types of things for you as well. All right, that's it for this video. We'll come back next time and keep talking more about chapter 10 and how conics relate to calculus. So I'll see you for the next video.